Yeah, perfect. Awesome. So we are live, and I'm already seeing here on my wow, already 20 people just jumped on board. So this is actually a fascinating talk that we're going to be doing. I want to give you a background why I think it's fascinating for several reasons. One is the individual himself today who is with us. That is why I think it's fascinating. And it's about the individual's personality. And to me, that is to us in the community that's probably the most important thing. The second, obviously, is the work that this individual is doing. So let me introduce myself for those of you who are not familiar with our live AI workshops. These are free workshops. My name is Terry. I'm co-founder of LiveAI, which is a training platform you may have known in the last 10 days. We may be making a lot of noise. I'm also CEO and co-founder of DeepCafa.ai, which is a research firm, focuses on artificial intelligence research in healthcare, in energy, in climate AI, and also lately in policy, which we believe is a very important topic, especially from an explainable AI perspective. Um, and obviously, we have a few other cool initiatives like Kura-A, which is a healthcare startup we launched outside of DeepCafa. In live AI workshops, what we do is we bring researchers who have done some awesome work in our community. So let's jump straight into the introduction. With me, I have Babak. Babak is I have been in touch with Babak for the last few years, and Babak has done. He's going to introduce himself, obviously. So I think what I really think is uh, extremely wonderful about this individual is Babak is extremely helpful, is a great researcher, and has done some wonderful work in healthcare industry and actually helped expand the healthcare industry dramatically. So, you must be familiar with this CAMELYON challenge that started back in 2016, 2017 timeframe. And it became a world-class sort of challenge that led the whole world, including ourselves, to use machine learning and deep learning to actually advance our models and our understanding of, starting with diagnostics and actually taking it to the rest of the world. Babak has done his PhD from Radboud Medical University, which is actually one of the top universities. For those who do not know, outside Europe, is one of the top universities that actually is collaborating together with Google and Kaggle and other platforms. But I would actually might even go a step further to say that I would say Babak probably was one of the guys who was laying the foundation of this great invention and exploration into machine learning and deep learning. But I want to give you the introduction to Babak. He does a lot of wonderful things besides obviously the healthcare, which he has helped not only revolutionize, but also popularize. So without much ado, I want to introduce you to Babak. Babak, tell us about yourself.
Hi, everyone. Hi, Terry. Thank you very much for your kind introduction. So my name is Babak Ehteshami, and I'm a staff engineer and manager at Qualcomm AI Research, and I'm currently in the Amsterdam office of Qualcomm. So the work that I'm going to be presenting today is on automated detection of breast cancer metastases using machine learning. This has been the work that I did during my PhD, and I'm happy to tell you about it. So do we have the slides? Are they being now? Okay.
But before we get onto the slides, obviously that was a very, how do you say, polite and a very compressed introduction. Tell us a little bit about your time you spent in Radboud University, and with all these wonderful researchers today we see also from University of Amsterdam. For example, Bas Failing, he's doing interesting things these days. So tell us a little bit about your experience. Because people want to look at you and say, wow, I mean, I want to be a data scientist like Babak. I also want to become a research manager someday like Babak. So a little bit of a background.
Sure. So I started my PhD in 2013. And at the time, maybe deep learning was just blooming in the computer vision and ML community, but not that much in the medical side. So I was working on basically pathology diagnostics of breast cancer, particularly. I was working with microscopic images and developing a couple of algorithms. So I started with a standardization algorithm, which I will tell you a little bit about in the talk as well. Which basically you have a lot of standardization problems in medical domain. You have data coming from different labs and from different hospitals. And because of the quality differences, it hampers the efficiency and efficacy of machine learning algorithms. That was the first topic I worked on. Then I worked on diagnostics of different types of lesions in breast pathology. I worked on the lymph node tissue section, basically metastasis detection, and organized the CAMELYON's basically challenge. That was on the medical imaging side, maybe the largest challenge in terms of the amount of data that you are providing to the participants. Over a terabyte of their data was given to them to train their deep learning models. And I also, towards the end of my PhD, I did a visiting research at Harvard in Beck Lab, where I've worked on prediction of breast cancer influences in its stromal patterns. So without looking at tumors, can we actually predict how aggressive the tumor is? That was the topic that I've worked towards the end of my PhD. And after that, I'm unfortunately not working in the medical domain at the moment. I'm working on more fundamental AI research. Currently focusing on efficiency because at Qualcomm we value a lot basically efficiency, and I currently understand how it's important to have intelligence per watt. So it's not only intelligence and having the most expensive model, but it's important how intelligent you are per watt. So that is the current focus of my research.
Awesome. This is great. Intelligence per watt. I know one of our researchers, we just published, or at least we put up our paper on Deep Kafa's research page. It was talking about using, and this is a researcher who's in Delft. And as you know, Delft, a lot of wafer and a lot of invention happens also at Qualcomm, obviously. And one of our researchers co-authored a paper in which we use this 0.7 voltage of energy to actually sort of train a neural network. Wow. I think indeed miniaturization and creating an excellent neural network that actually does not have to start eating the whole data center capacity will be a great way. And I think it's wonderful. So we are very excited to hear what you are doing today, but I really am because I'll tell you, Babak, I'll be very honest with you. When I read your research paper, I had presented your paper in Outreach. Outreach is not far from here in Assen, where I live. I live in the north of Holland. Outreach is a place where a lot of pathologists, histopathologists, convene once a year, German pathologists. So Outreach is in Germany. And I actually was taking pieces of your research paper, and I had shown how the algorithm had actually taken the task of, I still remember the number, 1,519 people versus one algorithm. And I shared this passionately with the people. So I think this is what we want you to explain, because a lot of people read papers, you download data set and you're playing around and you say, oh, I have 99% accuracy, I have 80% accuracy, but there is a big journey behind it. So go ahead. I'm presenting, putting your presentation up ahead, and let's get Babak started. Before you start, for the rest of the guys, if you're watching on LinkedIn, and I see many of you are joining on YouTube as well. If you're on Facebook, that's okay as well. Please keep asking your questions already. It's up to you. And once we are done having Babak presented his presentation, I will put your questions, as you can see here, just like this, for example. So, this way, Babak can read the questions and we can answer your questions together. And also from a beautiful home country, Babak, there's Saeed. Hi, Saeed Saberi from Iran. We love you guys. Hope everybody's safe there as well. So get started, Babak. We are very excited to hear from you.
Yeah, thank you, Terry. So, as you mentioned, I'm going to talk about automated detection of breast cancer using machine learning in today's talk. And I will, this is the agenda of my talk. I will start with briefly introducing what is breast cancer, how it develops, and then how pathologists actually do the diagnostics, and how we can bring AI to do the diagnostic tasks. And then I will describe you how we came up with the idea of organizing CAMELYON challenge and how it went, the winning AI solutions for the challenge, and the current state of the art in metastasis in breast cancer metastasis detection. And then I will discuss some of the directions that I see that are important for developing AI-based diagnostic tools. So let's start with breast cancer. Breast cancer is the most diagnosed cancer among women worldwide, and it's the second leading cause of cancer deaths. According to WHO, 1 in 8 women worldwide will develop breast cancer in their lifetime. So it's a very important topic, obviously. And if we want to look how breast cancer actually develops, we should look at the physiology of the breast. In the breast, we have mammary glands which produce milk, and milk is carried through ductal structures like this to the nipples. And the vast majority of the cancers start within these ductal structures. These cells start proliferating and cloning themselves, and in an abnormal way. And as long as they are inside the wall of these ductal structure, they are carcinoma in situ. They still need kind of treatment. But if they break this wall and get out to the breast, then you have invasive cancer, which is very dangerous. And one of the first things that pathologists would check is the status of lymph node, because after breaking into the body, the first point that this cancer develops to or spreads to is the lymph node, or they call it sentinel lymph node. So pathologists would take it out, check out these lymph node tissue to see any signs of breast cancer in there. If there is, it's a bad sign. It means cancer has developed the ability, and they would do more aggressive surgery there. So how does the diagnostics and treatment work for breast cancer patients? It's actually very similar to a large number of other cancer types. It starts with the screening. So most of the times radiologists would take a mammography or ultrasound scan, and then pathologists would come, and from the suspicious area, they take a biopsy and would inspect the cells under the microscope. They make a diagnosis, and if they see signs of cancer, then they would go ahead with surgery, and later stage medical treatments would start. But of course, as you see, the first two stages, screening and biopsy and diagnostics, involves a lot of reading images. And that's the perfect opportunity for AI as well, because AI is, at the moment, deep learning models are excelling at, let's say, vision-related applications a lot. And that serves a great opportunity to develop AI models for this task. But let's look at what pathologists actually do. So as soon as they get a sample tissue, they put it under the microscope, and they would inspect a number of things, like the morphology of the cells, the architecture of the cells. They would do a lot of other things, like inspecting doing molecular tests to understand the behavior of the tumor. So they have a very important role in this entire process. And traditionally, all these diagnoses are happening also still in the model world, in the Netherlands, in the US. In a lot of places, it's done on glass slides under the microscope. They don't really make digital images. But very recently, maybe since the last decade, you see some developments. People start digitizing these glass slides and producing these giant images. So this image is like 97K times 220,000 pixels. So it's a multi-gigapixel image, and if you don't compress it, it can be more than 20 pixels, basically more than 20 gigabytes on your disk space. So it's a very challenging data to work with, and also it is stored in a multi-resolution fashion, similar to Google Earth type of images. And the pathologist always looks at these images or even under the microscope in a multi-resolution way. starting with coarse resolution, finding out where suspicious areas are, and then zooming in. So one of the tasks which was very notorious and very difficult for the pathologists in the lab I was working at, and also it's a difficult task worldwide, is diagnosis of or detecting cancer cells in the lymph node tissue. It's a very challenging task. You have to recognize and detect these cells. And I've been talking to at the time I was talking to our pathologist, Peter Bolt, and discussing whether it would be possible to make a machine learning algorithm. And he was, of course, at the time, very negative, because we were not using deep learning at the time. And he was thinking this is almost impossible because it's a very challenging task. And he didn't believe that we could have a deep learning model that could do such a thing. We started working on that topic. And at the same time, we thought of organizing a challenge and inviting the international community to also tackle this problem. Of course, there was a lot of risks associated with it. The first one was the giant amount of data, a terabyte of data you're providing. And there's no guarantee people all over the world would start downloading such a huge amount of data. But the goal of this challenge was to evaluate novel algorithms for automated detection of metastases in lymph node tissue. And this was the first challenge in which we were providing the whole slide image. So these 20 gigapixel images were provided to the participants, and we had a lot of these images for them. And this task is actually of a lot of clinical relevance. It reduces the workload of the pathologist, obviously, because you can imagine we have these giant gigapixel images, and it could be that only a tiny fraction of this entire image contains cancer, and the pathologist has to go in high resolution, finding out when the cancer is. And there is also subjectivity in diagnosis, and by doing this in an automated way, we can reduce the costs significantly as well. So we designed two specific tasks in this challenge. The first one was that we are giving you an image. You just tell us whether it contains cancer or not. And this is a giant image. It could be that the entire image is full of cancer, and it could be that only a number of pixels contain cancer. So it's a very challenging task to say if it has cancer or not. And we evaluated it using, let's say, RUC curve and the area under RUC curve. The other task was lesion localization task. It's similar to object detection in computer vision community. And they not only had to find cancer, but they had to localize it and tell us where it's actually located. We evaluated this using the FRC measure. FRC is a measure widely used in computer-aided diagnostic tasks. So in there, we actually measure sensitivity with respect to the average number of false positives that are generated per whole slide image. For example, you would want a good algorithm to generate very little number of false positives, let's say one false positive on average per image, but have a very high sensitivity. And we had, basically, we averaged the score at several points along these false positive rates to give a score and rank the algorithms. And to collect the data, we went and wanted multi-centric data. So we had data from Radboud University and Utrecht UMC. And we collected a data set which was roughly a terabyte of data. And to annotate this is very important. To annotate these images, we went ahead and used expensive staining called immunohistochemistry, which is kind of superhuman because it knows exactly where the tumor is. It's expensive, so it's not really widely used, but it gives us a very precious ground truth, which not only we can evaluate the performance of algorithms, we could also evaluate the performance of humans. Because if the humans don't see that blue and brown staining, then they would be equal to how algorithms would perform. So we started the task, people started downloading and participating. We had a very good participation. And what we wanted from these algorithms was that you are given an image, you generate heat maps, you give us how likely is it that an image contains cancer, and also you localize these regions for us. For example, you see, so in these images, you see a lymph node tissue, and where is annotated, you see actually individual metastases.
Yeah.
Or here you see a region which maybe looks like cancer, but it is actually not cancer. But some of this algorithm has detected it as cancer. So that's a false positive, for example. Just want to give you an indication of how it looks like. So let's just start by some of the algorithms and their techniques. So this is actually the winning algorithm in 2016, and they had a very straightforward approach. They used the Google net, which, similar to ResNet, was one of the very good models at the time. And they would randomly extract patches from negative and positive slides. They train the model, and then they generate heat maps. But one smart thing they did a round of hard negative mining. They look at the training data and see which are the areas the network is making mistakes. Then they do a more smarter patch sampling in the second round, because they enrich the data with more difficult examples. They also did ensembling of two networks to make the networks stronger, which is commonly done in challenges. And they also did something smart for classifying the whole slide image. So typically among the participants of the challenge, what they usually did, they would classify all the patches inside the whole slide image, this giant image, and then they take the highest prediction that was assigned to a particular patch in the whole slide image. Let's say there was the maximum patch had the probability of 0.95. We assign that label to the label of the entire slide, and that is how we label the slide. But these guys did something smarter. They generated heat maps and then created masks out of those and extracted a bunch of handcrafted features, let's say, the old school way of doing that. Because the number of slides are not that much, then it's better to do maybe train a random forest. And that's what they did. And that gave them a significant boost. And this became the kind of standard from that moment on. After other teams saw that this is actually the best way, a lot of teams also did that. Something that they gave them boost was normalizing the whole slide images. And this was the algorithm that I had used, developed during my PhD. And basically, after using that, their ranking went from 4th to 1st. So it had a huge impact there as well. Hard negative mining and network ensembling helped them as well. This is another algorithm actually developed by Google, the Lena model. So they had kind of also an Inception V3 model, but they did something interesting. They actually fed multi-scale versions of the patch, so that the network not only sees something in the cells in the high resolution, but sees more of the context as well. They also did network ensembling, and they did actually multiple rounds of hard negative mining. They did color normalization as well, because that was becoming a trend. And they did the simple way of labeling for the slide. And that was like the maximum prediction across all the patches in the image. You give that as a label to the whole slide image. So you can assume that if you have a gigapixel image, you can have very noisy prediction, right? You can have one pixel which suddenly generates a high prediction, and could be very noisy. But their algorithm actually, as you will see, is so well that it still creates very reliable predictions. Something specific to their model, and maybe to the thing that it also creates a new way of sampling patches as well, was that they defined a novel way of extracting samples from negative and positive cases, because this is a heavily imbalanced data set. And they kind of found out that there should be a proportion that works best for them, like 20% from tumor and 80% for normal, while the majority of the teams would do 50-50. And they found it empirically. And actually, this way of sampling set a new a new line of approaches in the new teams as well. So the challenges is still open, I have to say. And in the highest rank that I currently see, the tricks that they are using are actually mainly focused on dynamic sampling. So the models, yes, they will take the most state-of-the-art models. Let's say, in this case, DeepLab V3 Plus, and they use it for segmentation, actually. And then they have a modern way of dynamic online sampling. So during training, they would find out which areas are more difficult, and they would enrich the training data with that. So the model becomes more expert to handle difficult cases. This seems to be the new trend on how to get the best result in the challenge. So we talked about algorithms, but how can we know if they give, as Terry said, some algorithms give an accuracy of 0.99. What do we know about it? What does it mean actually, 0.99? To get a good feeling of how difficult this task, we thought actually we give the same challenge to humans as well, to pathologists. We designed 2 experiments. First, we took an expert pathologist and told her, you have all the time in the world. This is the test set. Just spend as much time as you want and find all the tumors in these images. And it took her roughly 30 hours to diagnose these images. This is totally unrealistic in a clinical setting. In clinical setting, they're in a rush. They have to find as fast as possible. So we did the second study, and that was with a panel of 11 pathologists. And there they had the real clinical setting. So there was time constraint, and they had to indicate their level of confidence using 5 levels. Like, I'm definitely sure this is normal case. It's probably normal, equivocal, probably tumor, or definitely tumor. And with that, we could actually generate an RUMC curve and maybe compare them to the algorithm. And as I said, the pathologist would do their diagnosis on these pink and bluish slides. But we had a reference standard which nobody has. Like, the pathologist wouldn't see it, the algorithms wouldn't see it. So it would be a fair comparison. So let's start with the first task, which was metastasis detection. That is like localizing lesions. In this particular task, we are comparing with a pathologist which had all the time of the world to do the diagnosis, meaning in this case, 30 hours. The interesting thing was that, so you see basically sensitivity in detection versus the mean number of false positive per whole slide image. The pathologist very surprisingly generates 0 false positives, meaning that when she says something, it's impossible that it is wrong. When she says it's cancer, it is cancer. But the problem is that she misses a lot as well. She doesn't detect everything, but she's very good in not giving false positives. The algorithms, on the other hand, so the winning algorithm, for example, is very close at 0 false positive. But if you allow for a little bit of more false positive, let's say even 1 false positive in this gigapixel image, then it would outperform the human by a very good margin. And then here we also, so this was the winner, but we also have Google Lena's performance, the algorithm by Google. And there they achieve a surprisingly high accuracy of 91% compared to 71% of, compared to, 72% of the human, if they only allow for 1 false positive. So that means that they would basically detect the majority of these tiny lesions in the image. Let's go to the next slide. And also we did the evaluation, of course, on the image level classification. And here you see the ROC curves. At this part of the graph, we're zooming in this yellow area because the pathologists are all condensed on that region. Pathologists, you see the result of the panel of 11 pathologists. And all of these points are lying under the curve of the best algorithm. And actually both the first and second algorithm, which means that all of them got beaten in this challenge. And this is the operating point of the human who had all the time of the world, the green. So it is as good as the best AI algorithm. So if you have unlimited time, then you are as good as the best model. And we also compared it to the average of the panel. So the average of the panel has an ROC curve, which is shown here. This is the maximum. This is the lowest AUC. And you can see also the ROC curve of the pathologist without time constraint on the green curve. And in terms of AUC, the winner had an AUC of 99.4. The pathologist had the AUC of 96.6. and Google's model had the AUC of 99.3. So they were beaten by a very high margin. So these are some example images from the test set. So this is an example where you actually see the tumor. This is a very tiny tumor, by the way. There is a yellow annotation around it. This is an example which the winner algorithm could find, but the pathologist actually missed it. It's a tumor. Another example, this is very difficult. I still get shocked where the tumor is. The tumor is actually located here. These cells are only
unbelievable.
Yeah, and the winner algorithm did find it, but the pathologist missed it. And you can see it's a very tiny fraction in this giant image, so it's very easy to miss. But something that was still some algorithms might struggle is that, for example, this is an artifact in the image, like a piece of torn tissue. For the pathologist, this is super obvious that it's not tumor. But mistakenly, the winning algorithm says this is a tumor while it's not. So pathologists never give false positive, but they do miss. But the winner algorithms, the best algorithms, are exactly the reverse. They kind of detect a lot with very little number of false positives. Now the question is, we have these AI algorithms. How can we actually help pathologists in real clinical practice? We know that algorithms are reaching human level performance, but if we bring this AI to the lab, would it actually help, or is it like only in numbers? And there are two settings in which AI could help. It could maybe first do the diagnostics itself all alone, and then tell the human, okay, these are the ones that I think are tumor. These are the ones, the red, I'm sure they are normal. Just inspect the tumor. And the ones that I'm uncertain, let's do the expensive staining, and you would check those. So this is one way. And the other way is that they look at it simultaneously. So the human would see the result of AI, and they make a decision together. Well, the good thing was that Google actually went ahead and did this clinical study. They took their Lina model, and then they conducted the study with a pathologist. They basically grouped them into two groups, and then they said, your first assisted, go with the AI, do the diagnostic. Then they have a washout period of 4 weeks. Then they would do the diagnosis again without the AI assistance, and they would compare how the performance of AI alone, human alone, and AI plus human changes over time. So this is how human would get assistance. They would get, let's say, contours around the tumor, and they would know which areas are suspicious. This way, they're barely ever missed then. So, and this is the conclusion. Based on the results, they found that algorithm-assisted pathologists demonstrate higher accuracy than either the algorithm alone or the pathologist alone. And it's a surprisingly high accuracy, 91% sensitivity compared to the 83% of the human pathologists. Also, in terms of efficiency, a slide containing micrometastasis, so small metastasis, was diagnosed in only 61 seconds compared to 116 seconds that pathologists usually spend. So the time was made half, but then the accuracy was also a lot higher. So this shows the merit of actually combining AI with human. But then they took it even a step further, and they made them a kind of a microscope. So the microscope is something that pathologists are very used to. They mounted a camera, and a camera would simultaneously look at the same area that the human is looking at. And then there is an AI engine which runs the same model, and live in real time would tell the human where actually the tumor is. And then as the pathologist is making his diagnosis on the slide, he would see the contours generated by the human. And so this was incredibly exciting to me to see how it is going, this lymph node challenge. And the interesting thing is that the model as is, so they didn't actually retrain, and it works in these new images as well. And they got a field of view area under RC of 0.98, which is which is very high. And here's a video that I want to show that how this process works.
There's no cancer treated without understanding what the pathology is.
The tissue slides that pathologists use to diagnose cancer contain a vast amount of information. It's very time-consuming, very fatiguing.
Every cell needs to be examined. Sometimes cancer is very difficult to recognize.
We had the idea for the Microscope project about a year ago. It brings augmented reality into an existing microscope to detect cancers in real time. We're bringing AI directly to the user and meeting them where they are right now.
I think this is going to enable almost all pathologists to have access to machine learning.
Just a few weeks ago, we got it working end-to-end.
It has a camera, so it's seeing the same thing I'm seeing. Information is being fed into a computer, which is doing billions of calculations and telling me that's the tumor, that's not the tumor.
Right now, it detects breast cancer and prostate cancer, but it could also work on any other cancer type that we train models for. The knowledge that you're getting when the microscope points out cancer to you is the knowledge of many pathologists who contributed to training the machine learning model.
We had a team of pathologists that went through thousands of images, teaching the computer what cancer cells look like.
I think it has been very effective at locating areas of concern. It's like getting a second opinion.
It's going to make the doctors much quicker. They're going to make them better, which is going to overall benefit the patient.
The mission is to increase the accuracy and availability of cancer diagnosis and save people's lives. I can hardly think of anything that's more motivating.
Cool.
So now the question arises. We saw that standalone AI was doing extremely well. And the question arises whether we need to actually replace humans completely, because they can, on specific tasks, they can actually outperform humans. Why do we need humans at all? And we know that deep learning models, the models that we are training, especially in a supervised fashion, they are working extremely well. But the problem is they are working extremely well on isolated diagnosis tasks. Like you give it a binary task or a categorical task, and it excels at it. But our current models do not have the breadth and the contextual knowledge of human experts. For example, while diagnosing these lymph node tissue sections, it might be that there are some rare findings in there, like lymphoma, infections. And these algorithms are not trained to find those. And these are also typically very rare cases, which there is not a lot of training data for them either. So you would, in this perspective, if you consider the breadth of knowledge that a pathologist has, it would almost be ideal if they are actually combined together. Mm-hmm. And as we saw in this study by Google, clinicians can be empowered by AI because their accuracy is going higher, and the time they are spending on reading images is becoming half. And it kind of combines the strengths of humans and AI. So humans seem to be bad and in finding all the details, because your vision would get exhausted, and you will have habituation. So you easily miss. While AI is excellent in finding all the details, they never get exhausted, but they might generate false positives. And humans are excellent in rejecting false positives, so they exactly combine each other. Something that I'm kind of considering in my mind, how do we want to go with the problems that are arising in healthcare? We see that a lot of these models, for a lot of these tasks, we define a specific task, cancer versus non-cancer, for example. We get the pathologist to annotate a lot of data, and then the model does very well. But there are so many, maybe thousands of tasks in just pathology itself, that it becomes impractical to annotate a lot. There are a lot of cases which are rare, a lot of diseases which are rare, and we may have limited amount of annotations. And as you know, in the computer vision community, we have these ImageNet data set. And surprisingly, even pre-trained networks, if you take the weights of ImageNet and applies to these models, it still works very well. So it would be a very good idea, I think, in my opinion, to have kind of a model that learns in a semi-supervised or self-supervised fashion, that would work across different tissue types, because breast doesn't overall look that much different from prostate, for example, or the cellular features could help each other. So you don't need to get a lot of annotations for every tissue you want to work at. You can learn a lot of these in an unsupervised fashion. You could improve each other by learning, maybe by doing multitask learning. For example, if for colon you have very little data, you could do multitask learning of classifying breast and colon, because the features that you are learning for classifying breast are going to help colon cancer as well. So these are, I think, some of the directions that we should be looking into if we want to go further with diagnostics and have a more generalized solutions that maybe ultimately could replace humans, but we are definitely not there at the moment. So now I want to have a step back to say how this project started and how it went. So in 2016, I was talking to this pathologist who did not believe actually that much that it could be done. Actually, I have to say I was also skeptical that it would work so well. And at the time, there was actually no automated solution available that works well. And we started to kick off this challenge, and we were working on this task ourselves, and simultaneously encouraged a large community to come and participate. And within a couple of years, it's 2020 now, we have hundreds of algorithms which are working for this problem. And the leading algorithms are currently outperforming humans. And after that, we do see that, for example, Google has already done clinical evaluation. They have set up studies to see if pathologists would benefit from that. And they saw that they had improved accuracy and efficiency. And now, in such a short amount of time, you see that, for example, an augmented reality microscope is already created. And there are multiple companies which are actually having their own solutions, commercial solutions, for reading lymph node tissue sections. So it was very nice to see that over the course of these years, a problem was brought to the attention of the community, and then to a very good extent solved. But still, of course, a lot of challenges remain, like handling rare situations. Of course, this wasn't done by myself alone. There was a lot of team members who helped me in this entire process. And a lot of collaboration with different institutes, with Philips, with University Medical Center Utrecht, TU Eindhoven University, and other organizations that I need to thank. And with that, I'm actually very happy to take your questions as well.
Wonderful, awesome presentation, Babak. I listened with great interest, as much as I read it back 4 years ago when I saw this paper publish, and read it also with great interest back then. Since then, obviously, you know, this has dramatized the adoption of all these projects and competition. After that, you know, you've seen Golden Bowl projects on Kaggle, where you had 2D and then there were 3D images with lung scans. Exactly. I also think, and I believe in Radboud, they have already experimented with using a machine learning model learned on one tissue sample, and with reasonable accuracy used it on a different morphology as well. I've read that as well.
That is true.
Yes, it was very interesting because essentially, I think, you know, this is me, this is my body. I mean, it consists, I have 3.7 trillion cells on my body. The correlation of a cell accumulation and aggregation around my heart might be very different than maybe on my prostate, but there may also be similarities which could be used and learned on those areas. So wonderful. I'm going to start asking a few questions which people have. Maybe I'll just post questions, Babak, and see if you can answer these.
Is there a higher risk to women who have babies versus women who do not have babies in real life? I'm not sure if this information is tracked or not. So regarding breast cancer alone, I think it is the general thought that women who do not have babies in their lifetime maybe have slightly higher chance of developing breast cancer, if I remember. Yeah.
Interesting. That's an interesting insight. Let's see what else questions. Yeah, this is interesting as well. So Joseph has a question.
Okay, what is the adaptation rate of ML for breast cancer detection? That's a good question. I think for we need such kind of initiatives to bring this to the attention of the pathologists, that this could actually be ready for use. On the lymph node tissue side, for breast cancer, our hospital in Radboud, our pathologist, the one who was skeptical, is already using the AI algorithm we developed in his routine diagnosis. It is also AI assisted. He doesn't rely on it alone. He has to look at the results at the same time. On the breast cancer side itself, there are particular challenges. For example, for detecting different grades of cancer, or for differentiating DCIS, let's say, from invasive cancer. There is a lot of work done, but I'm not aware that we have a fully automated solution that is relying only on the automated model. I think there is always an AI-assisted aspect to it, and there are companies that actually do offer services. So they get the image data, they run the model, and give the result to the hospital.
Cool. I guess this is a debatable question. I'm not sure if you want to answer this.
My question is diagnosis of COVID-19.
It's on COVID.
So I do not know much about diagnosis of chest X-ray for COVID-19. Actually, from the group that we were at, I know that they were working on this project as well. So what they did, so they have a lot of models that run on CT for a lot of tasks, let's say for tuberculosis detection, or for finding lung nodules. And they could actually fine-tune these models on some limited data from COVID-19 and get very high accuracies. I know that there was a joint effort actually in the Netherlands, and they got it to a very high accuracy, and there was a recent publication on that. So you could actually, a lot of these models could be very easily transferred, because the features you would learn in one task would help the other task as well.
Perfect. Then we have this question.
What open source packages did you use to develop the solution? Okay, so for deep learning part, almost everyone used Python, and including myself. Also, I provided tools for reading the images or standardizing the models. For the standardization of the data, I developed it in C++, but the entire development of the deep learning part, training the models, were done in basically Python, using deep learning libraries like TensorFlow or PyTorch.
Cool. And then we have, okay, yeah, this is interesting as well, but I guess, yeah, the techniques are changing these days.
Leprosy and rare diseases. So this is a very challenging topic, I would say. So what I think one thing that you could do when you have very limited amount of data is doing things like self-supervised learning. You could, for example, have generative models like variational autoencoders that try to regenerate the data. So they get a patch and they try to compress it in some sort of essence information, and using those compressed features, reconstruct that image. And that kind of forces the network to learn the most important features. And if you don't have a lot of data, you could use generative models to kind of learn features which could help in diagnosis. Or you could actually make your learning situation like a weekly supervised. So if you don't have labels, let's say annotations for the specific tumor, you could say, okay, I know that this is a picture that the whole image contains cancer. I don't know where it is, but I know that there is some cancer in there. So it would be a weak label. And you can get these kind of label actually very cheaply from the archive. You could get the archive because some patients have cancer. You scan them and you have a lot of kind of weak label data that could be very useful for semi-supervised and unsupervised learning.
Cool. Amit Pandey has a question.
Does the reverse situation work? That has given the heat map of genes, can we predict the occurrence of breast cancer and reoccurrence?
It's an interesting question.
So I don't completely know what the heat map of a gene is actually.
So let's say that it's more into molecular biology, which probably, or genetics, I think, which, yeah. But it's interesting question.
I think it's an interesting question. So one thing that I did toward the end of my PhD was looking at the areas surrounding the tumor, so not the tumor itself. These areas are called tumor-associated stroma. So it's the connective tissue, and apparently it changes some sort of pattern that you could not, the pathologist would not visually can quantify it. So they know there is something there, but they cannot say if it is aggressive or it's an indication of a progression or something. So we did an analysis using deep learning models, extracted features from those, and we're able to actually predict how aggressive the tumor is based on that surrounding tissue. And of course, you would definitely enjoy a lot, where your model enjoys a lot if you can feed in some genetic data or molecular data to enrich the information it has, and probably giving more, let's say, reliable prediction about the survival of the patient, or the opportunity of getting a recurrence. Actually, I think that would definitely be possible to use genetic information.
I guess this is very debatable. People are inventing all these models. Today, in fact, I saw one research paper. Let me start by answering this, and I'll let Babak finish it. So Hadi, there was one paper today that is called low shot. So meaning, you know, there's 0 shot, 1 shot. There's I saw today on arXiv low shot. So I'm not sure specifically from the pathology perspective if 1 shot or other, let's say, faster inferencing and generalization models can be directly applied where you would want to create a human-centric sort of algorithm. But I would say, at least from a pathologist perspective, who I am not, I would say, I think it's better to use reliable models. What do you think, Babak?
I totally agree. I think for clinical data, well, one-shot learning is a very interesting kind of method in terms of the ML research, I would say. But I don't think it has been successful enough in the medical sector. And for the medical kind of data, you need super reliable predictions, and especially if you want to rely on that. And I haven't seen much work on the 0-shot or 1-shot learning for pathology or medical data. But there might be some that I'm not aware of.
Yeah, maybe I can add a small joke to it. You cannot apply YOLO if you know that YOLO also means you only live once. So if you apply you only look once model on someone where you may do a misdiagnosis, then it might be a problematic situation. You know, there are a few more questions, and I think these are wonderful questions. Maybe we'll just answer one last question, and I would like to summarize it. So let me just take, wow, these are great questions. What I'm going to do is actually, I will post these questions here, and then I will unpost them, because these questions we will let Babak answer. Maybe we'll create like a Q&A where Babak can answer these questions on that page. So definitely, and then I'm going to just post this as well. So I know I will remember when I look back at this video. That's the best way to do that. And then I'm going to also, Fatime, our researcher, she's also here. I'm posting her question as well. It's a very important question, Fatime, especially as a young woman. You know that biopsy is a complicated procedure. I totally agree with you. And Vikram, I'm posting your question as well, because this, I think, is a very good question as well. MTL is something which I know Babak is learning and working on. Continuous learning, lifelong learning are fascinating topics, which is where, bringing this whole human-centric AI will become very interesting. But I want to end this discussion with this. And I read your paper with great interest and also great detail, when we were looking at, when is the capacity of a human being exhausted because of, how fast can I go, and look at those false positives. And I used a term called lost positives. So especially when you have these huge dimensions, these huge images, these DICOM or other formats, the biggest problem is not, and that probably might answer Amit's question a little bit as well. So you're just using various techniques like region of interest, etc. But I think as our human body is evolving, our consumption patterns are changing, the way we are consuming food, our morphology is changing as well. I think the pursuit of lost positives, or in a big tissue sample, as you were showing, Babak, where you just kind of under a certain sort of a nanopixel, a human eye would just not be able to notice it. Even a medical device I have known are able to miss those, unfortunately. But I think what I would like to sort of summarize is there's a long way to go, but I still believe that in the last 5 years, we have made tremendous leaps in terms of bringing technology into the hands of radiologists. And hopefully from there, we can dramatically increase, provide the capacity to our already under, let's say, represented and also heavily subsidized and understaffed medical institutions. So it's a win-win, if you ask me. But again, I'm a technologist. I love technology. I've learned a little bit about this, and Babak, as you can clearly see, has spent a lot of time doing this. So my words would be, let's continue to keep building models that are reliable, that are reproducible, that are continuously explainable and interpretable, so we are able to build confidence with the medical community that I can reproduce this. It works with a reasonable confidence. I am so great at finding out the false positives, because that is what I'm so good at. But I have an assistant that helps me search for those lost positives, and if I can find them, I've done a great job. What do you think, Babak?
Exactly. I totally agree with you. You put them very nicely. They combine, humans and algorithms are combining each other very well this way. Something that I think still is underappreciated. So I'm a, let's say, research scientist working on machine learning. So I love the algorithm side of things. But something that is very important, there has been a lot of good algorithms, but bringing them to the level that can actually help humans is not trivial. It's just presenting a heat map to a radiologist or a pathologist is not that useful. It could be quite messy how you present the information and how you want to actually save their time and improve their efficiency and accuracy is non-trivial. So we shouldn't only look at the deep learning side of things and make our model better, but also we have to learn how to translate it in a way that could bring these improved care as well. And that is actually only possible if you work closely with the clinicians and actually can understand what they want and how they can be empowered.
Perfect. With that, ladies and gentlemen, thank you so much. It's been so fascinating. I have literally a lot of people who came here. Even in the end, I see many of you have stayed. That's amazing. So that actually is a testimony that, Babak's work in his academia and what he's currently doing, which is a huge topic as well. Maybe someday we'll do another workshop on continuous learning, multitask learning, learning about all these other techniques that fortunately, hopefully, will also become useful in the AI industry in the coming years. Efficiency, as you said, efficiency on whether it is on a nano sort of scale, and how efficient your models can be on processors and chips. So that's a fantastic work you're doing, Babak. I appreciate it. Thank you so much.
Thank you for having me.
This was great. Thank you very much. We'll have more sessions with Babak. You can reach out to Babak. He's here on LinkedIn. He's extremely helpful. I haven't met a person, and that's what I find amazing about the quality of researchers like Babak is they're open. They keep their mind open. They take so much effort in helping you. And if you're a fellow researcher, engineer, developer, data scientist, or someone from medical professional who has questions or doubts, do please reach out to him or to us, and we'll help you with your questions. Thank you, guys. Take care. Babak, thank you. Have a wonderful weekend. Just hang on, Babak. I want to thank you personally once I end this broadcast. So see you guys, and have a wonderful, wonderful day.